I don't have time to run down to the water fountain and get a drink before that thing engages. Okay. Absolute value of 4x equals 12. This splits into two equations because it's true. If 4x is equal to 12, then the absolute value of 4x is 12, right? Well, 4x is equal to negative 12. The absolute value is still equal to 12, isn't it? So we split this into two equations. Negative 4x equals negative 12. And 4x equals 12. And we solve both of the equations. And it's really easy to solve. We get x equals negative 3. X equals 3. There's an or between these. And I really would like to see that word or because it explains the logic of the solution. If you're not putting that word or in there, I did last time, okay, when I introduced this, try to do everything you see me do because there's a reason for it. It reinforces the difference between or and that's very important in these equations. However, most people just split into two equations and wrote down the solutions. Some people just wrote down the two solutions to this one. That's okay because you see, you understand that there are two solutions. However, when we get down to this one, we really have to write it out a little more formally. Oh yeah, in the solution set. Is the set negative 3. There's our solution. Now I accept this, but that's really a standard way to write a solution. With all solutions in set brackets. Okay. Now, absolute value of 3x plus 9 less than 5. Well, that means now this splits a little more subtly. Okay, let's think about it. If 3x plus 5 is too big of a negative number, then this absolute value is going to be greater than 9, right? Like if x is equal to 100, then you got 300, negative 100. You got negative 300 plus 5, negative 295 here under the absolute value sign, and 9. Absolute value of negative 295 is not less than 9. Okay. Well, actually, when I write this, I just do a little differently. I'll say it this way. It's between negative 9 and plus 9. Okay. Meaning between negative 9 and 9, any number between there is greater than negative 9 and less than 9, right? So if this number, 3x plus 5, is between negative 9 and 9, then it's greater than negative 9 and it's less than 9. Okay. Now we can solve these inequalities. So you get x is greater than negative 14/3. And x is less than 4/3. Now the details of solving it are simple. So I'm not going to belabor just solving what's just a linear inequality. But we've got two of them here, and they're connected by this and. This means we could write this as a compound inequality. It means x is between negative 14/3 and 4/3. There's x. It's got to be greater than this one and less than this one. Okay, so it's the interval. This is not a point. I mean, that's the same notation you'd have for x and y coordinates of a point, right? So we got to specify that it's the interval here. And we could graph that. We put negative 14/3 here. And 4/3 here. Which could be maybe about here. And we then shade this interval with an open dot on each end, indicating that we don't include negative 14/3 and we don't include 4/3. Because if x was negative 14/3, the absolute value would be equal to 9. It's got to be less than 9. Okay. And if we did the negative 14/3, we'd have a number that's equal to negative 9. It wouldn't be. So the absolute value would be equal to 9, not less than 9. Okay. Now that whole process, that's what open math asks you to do. You really need to be able to write out that process and preferably do it logically, because if you don't write out the logic, you're going to be vulnerable to making mistakes. Okay. You want to reinforce the logic of this with the and. It's got to be both of these. Okay. It's got to both be greater than this, and it's got to be less than this. So it points out here that are greater than negative 14/3, but if they're not less than 4/3, they don't count. Okay. And same sort of thing on the other side of negative 14/3. Well, let's go ahead and you know what? Being careless, I just wrote this out here where it was, and half the board wasn't visible. So let's just, most of the work here was visible, but let's make sure we see all the details. Okay, here's the problem between negative 9 and 9. It's got to be greater than negative 9, and it's got to be less than 9. We solve it and we graph it. Just the way open math shows you how to do it. Okay. So now the last one, and we really have to be careful of the logic and several details here. Okay. What's it mean for the absolute value of a number to be greater than 6? Well, this means well, 4 minus 2x is greater than 6. We're okay, right? But also, okay, if 4 minus 2x is less than negative 6. Like if this 4 minus 2x is negative 7, then we have absolute value of negative 7, which is 7, and it's greater than 6, right? So we get into values of x that make this into big negative numbers. They all work. If you get a big negative number here, the absolute value is going to be greater than 6. Okay, well, let's write this out. Okay. X could be a solution to this equation, right? Or it could be a solution to this equation. Okay. It can't be and, because no solution to this equation, no solution to this inequality is a solution to this one. There can't be a solution to this and this because it will be a solution to one of them. Well, no, it's pretty easy to solve these. You just use the rules for inequalities that we covered some time ago. You're going to get, I'll do it formally. Subtract 4 from both sides, you're going to get negative 2x less than negative 10. And then we're going to divide both sides by negative 2. And realize that when we divide by a negative, we have to reverse the inequality. We can't forget that. If we don't reverse the inequality, we're going to get something that doesn't make sense. So when x is bigger than 5, its absolute value is bigger than 6. Okay, now think, if x was equal to 5, just to check this, if x is equal to 5, then 2x is equal to negative 10. And 4 minus 10 is negative 6, right? So you'd have negative 6 here. Well, x has to be bigger than negative 5, but the bigger x gets, the bigger 2x gets, and you're subtracting 2x from 4. So subtracting a bigger and bigger number from 4. If x is 5, we're equal to 6. We're not exactly greater. We're not yet greater than 6. But if x is bigger than 5, this is going to be a bigger negative number, and the absolute value is going to be bigger than 6. Okay. Well, or all right, that's 4 minus 2x greater than 6. I'm going to decide how much to write out. I didn't even do anything. 4 minus 2x minus 4 is greater than 6 minus 4. Well, that gives us negative 2x greater than 2. Divide both sides by 2, negative 2. And you get x here, and you get negative 1 here. It's got to be less. Okay? X is less than negative 1, we have to reverse the inequality. Now, if x is negative 1, 2x is negative 2, and 4 minus negative 2 is 4 plus 2, which is 6. So that's kind of a check. And then we check what happens if x is less than negative 1. Well, that gives you a bigger negative number here. But it's being subtracted from 4, so you end up adding a bigger number to 4, and you're going to get something bigger than 6. If you can think that way, it's helpful. Okay? So, you know, this or continues down here. It's this or this. Now, if you want to graph that, it means if you got 5 here, negative 1 here, okay, x can be bigger than 5. Well, x bigger than 5 is this interval, all number bigger than 5. You got the open circle on 5 to make sure that you don't include 5. And we have this for x less than negative 1. So here's x greater than 5. Here's x less than negative 1. Why do we say or? Well, if x is here, it's okay. If x is here, it's okay, right? So if x is here or here, we have a solution. X can't be here and here. And what you want to do is, a lot of people are going to want to say this and this. Logically, it can't be both. Now, what you're doing, and the reason you might use and is, well, we use this interval and this interval. Yeah, we did. Okay, That doesn't describe where x is, though. Okay, you put down this interval and this interval, and then we say, well, x can be in this one or in this one. It certainly can't be in both. You want to get straight on the meanings of and or, and it can be subtle, it can be confusing, and it is in this case. Okay, as I said, you're going to use this interval and this interval, but x can't be in this interval and this interval. It's going to be this interval or this one. Okay, it's worth thinking about. Okay, I think I can find what I've got here. Okay, power functions. Power functions are of the form y equals x raised to the power p. Hold on, I still don't have the top of the board. Okay, let's try this. Okay, that'll work. Sorry. Okay, y equals x to the p. Okay. These 5 are toolkit functions. Toolkit functions are pretty heavy on power functions. Okay. And what do the graphs of these look like? Those things can be constructed in a 4x4 rectangle. There's our squaring function. Now our cubing function, we need to go up to 4x8 rectangle. Cubing function, and let me draw this in a different color. And you should recognize this. There's your cubing function. Your x to the 1 function. Okay, well, we've got the square, we've got the cube, we got the first power. We could do x to the 4th. It looks a lot like x squared, but it gets flatter at the bottom. So you got this picture. And then, of course, we have the negative powers. This is y equals x to the negative 1. X to the negative 2. And these are kind of the basic shapes of power functions. You'll see more shapes of power functions, like X to the fourth looks a lot like x squared, except it gets flatter in the middle. And it goes up higher here. Okay. X to the fifth looks a lot like x cubed, but it's steeper here and flatter in the middle. X to the negative third would look a lot like this, but the curve is a little bit differently shaped. Okay. And it goes closer to the origin here. So there's more we could say. Okay. There's a lot I could say about power functions, but I don't want to give you more than what you need right now. I mean, I want to, but it's rather better for you if I don't. Okay. All right. Now let's get over here as far as we dare. Okay. And of course, I didn't mention it, but we do have the x to the 1/2 or the square root function. Okay. And the square root function going to require a different color. Looks something like this. I didn't quite draw that right. Square root is x to the 1/2, because if you square the square root of x, you get x, right? If you square x to the 1/2, you got x to the 1/2 times x to the 1/2. Add the exponents. 1/2 and 1/2 is 1. You get x to the 1. That's x. So you square this, you get x. You square this, you get x. They must be the same thing. Okay. We'll talk more about fractional exponents later. All right. And you probably already know that the square root is the 1/2 power. Maybe you didn't really think about why. So you can have fractional exponents. Anyhow, polynomials. Have sums of multiples of power functions with integer or with whole number powers. Okay. Well, examples. Y equals x squared plus 5x plus 7. What power of x do we have here? Show me with your fingers. Is that an integer? Is that a whole number? Yeah. What power of x do we have here? Careful which finger you use. Yeah. Okay. And what power of x do we have here? 0 power. X to the 0 is 1. That's 7 times 1. That's 7 times x to the 0. Okay. It's fairly easy to understand. That 0 power thing may be a little fuzzy, but I think you get the idea. Okay. Let's try this one. Okay. Anything in there that isn't a multiple of a whole number power function? No. That's the power function of the exponent 4. Here are the exponents 3. Here are the exponents 2. Here are the exponents 1. Here are the exponent with the 0. Okay. So that certainly fits. And it's a sum of multiples. We add 9x to the 4th and we add negative 15x cubed. Okay, that's a multiple. And we have 738x squared, that's a multiple. Minus 15x is a multiple, and of course 19 is a multiple next to the 0. Okay, how about this? Is that a polynomial? I'm seeing dark looks. No, I don't think so. And I'm saying, yeah, okay. Okay. So, what do you think? How many think it's a polynomial? How many think it isn't? Okay. Well, let's discuss this. We're going to put the pressure on people who think it isn't. Okay, well, this is a polynomial. So let's just distinguish both this one and this one are polynomials. This is not a polynomial. Not a polynomial. Square root of x is x to the 1/2. That's not a whole number power. Put this here, and we'll say, nope. Not a polynomial. Okay, let me write one more up here. How about that? Is that a polynomial? We're going to vote. Think about it for a minute. Okay, how many think it's a polynomial? Okay. Yeah, all the powers are whole numbers, right? Anything wrong with it? How many think it's not? Well, it's not. It's not a sum. This is a sum of multiples. The numerator is, and the denominator is a sum of multiples. But when you divide a sum of multiples by a sum of multiples, you don't get a sum of multiples. Okay? So the numerator is a polynomial, denominator is a polynomial. This is not a sum of multiples. Kind of poorly, but it's not a sum of multiples of power functions. Well, that's badly written. It says nope. Okay, this is what you call a rational function. You want to store that away. It's like a ratio, it's something over something, right? Something divided by something. It's a ratio of power functions. It's a rational function. Okay, and these are coming up pretty soon. But first, we want to nail the polynomials and see how we deal with them so that we learn how to deal with rational functions. And this is where, if you add two expressions like this, well, you'd better know in detail how to add fractions. Okay. This is why we started the course with fractions, because adding rational functions is a little bit hairy. And it's really impossible if you don't know the rules for adding fractions. Okay. Okay. Well, let's learn a little bit about a polynomial. Now, of course, we know a lot about quadratic polynomials. We know how to find its zeros. We know how to find its y-intercept. Okay. We know how to find its axis of symmetry. We know how to express it in vertex form. Or if we don't, we will in the next section. Okay. And we've set ourselves up to understand that very well. Okay, there's a question I want you to think about it in both. Is the quantity x minus 5 times the quantity x plus 7 a polynomial? Didn't have time to start dancing, but almost. Now, this is polynomial. Yeah. Okay. We can use the distributive law to multiply this. And I'd rather see the distributive law than this and this and this and this. But I'll tolerate that because I certainly used it when I was in high school. Okay. And I nailed my algebra real well. But you want to see how it comes from the distributive law, because sometimes you really need to use the distributive law and be able to write it out. We'll emphasize that as we go on. I think we only have to some extent. Okay. This is clearly a polynomial, and this is the same. So this is clearly leave myself room to write it all out. This is clearly a polynomial. And this is the same as this. Okay, they're the same. They have the exactly same value for any value of x, so they have to be regarded as the same. Plug in any number for x here and plug the same number in for x here, you're going to get the same result. Okay. Now, an advantage to plugging numbers in here is you never have to square anything. Okay. So sometimes arithmetic is easier if it's factored, but the main reason that you want to see the factor form, this is factor form. Let's label them terminology. This is the factored form, and this is the expanded form. Okay. You learn more from the factored form than you do from the expanded form. And that's the reason people talk so much about factoring. It's probably the main reason they think it's important. I don't think factoring is all that important, but you know, it's part of the course, so we're going to learn to do a little bit of it. And you probably already know how to do a little bit of it. There are some fancy tricks you can use for factoring that never, ever, 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 ever get used by anybody except theoretical mathematicians. How many of you expect to be a theoretical mathematician? Probably not something you'd be interested in doing, okay? And out of the population, fewer than 1% of the population even has the brain structure to do it, okay? Yeah, you got good brain structure, you wouldn't be here. Okay. You don't have the brain structure to be a theoretical mathematician. I don't have the brain structure to be a theoretical physicist, be an experimental physicist. Okay. But my advisor spent 2 years convincing me that even though I was doing pretty well in physics major courses, I didn't have what it takes to understand the really big stuff. Okay. And almost nobody does. That's like one person out of 10,000 or 100,000. Okay. Put me in with 10,000 people. On the average, is going to be one who's smarter than me. So I can't be a theoretical physicist. That's a joke. There'd be more than one. Okay. Expanded form. Factor form. Factor form is important, but you're never going to be able to factor most polynomials. Still, by looking at the factor form, we can understand things about polynomials. Okay. For what values of x is this equal to 0? Can you use your fingers and give me an answer? Yep. There's 1. Okay. Yeah, I'm seeing 5 and 7. Of course, the 7 have to be negative, right? But if x is 5, you plug in for x, you get 5 minus 5, that's 0. And you multiply that by whatever 5 plus 7 is. Now, that one person out of 10,000 is smart enough to know that that's 12, but I wouldn't. Okay. It doesn't matter what that is. As soon as this is 0, you know it's going to be 0 when you multiply them, right? And if x is negative 7, there we have it. The problem with negative 7 is people are flashing 5, 7, 5, 7. Got to be 5, negative 7. Okay. And you know that. It's just that I threw something at you that you couldn't represent with 1/2. If it was negative 5, you could do that. Okay. Okay. Well, it's obvious. Okay. How about the solution of what we did here is actually the solution of this equal to 0, right? So we're actually asking the same question, but a little differently. Okay. How many solutions do you think you're going to find? Can you give me one of them? I think you need a negative. Yeah. Okay. Oh, 4. Because if x is 4, 2 times 4 is 8, and you subtract 8, you get 0. And that's multiplied by everything, so it makes the whole thing 0. Okay. Well, is there a number that makes that 0? Negative 2, right? Okay, well, we can be a little more formal about this. Like with absolute values, splits into 2 equations. 2x minus 8 equals 0. X plus 2 equals 0. And there's a big or between them. It could be this, or it could be that. Well, the solution here, and we just do a couple of steps. This is easy to solve. X equals 4. x equals -2. We do it by formal algebraic steps. Usually write the numbers in order from least to greatest. Okay. This makes it easier for people to read. Okay, well, what's this tell us about the graph of this function? Graph of 2x minus 8 times x plus 2. There are 2 points I can immediately put on the graph. If x is -2, that makes y 0. So we put the point -2, 0 on the graph. And if x equals 4, y equals 0. That means that the point 4, 0 lies on the graph. Okay. What else can we do? Well, what if x equals 0? Well, if x equals 0, we'll point to this one up here because it's a little easier to read. If x equals 0, this gives us -8, and this gives us 2. And -8 times 2 is -16. So we have the point 0, -16. We know that when we multiply this out, we're going to get a quadratic. I mean, we're going to get what? 2x squared minus 4x minus 16. Y equals 2x squared minus 4x minus 16. We know then that that graph has to be a parabola. And we know that a parabola is symmetric around its axis of symmetry. The axis of symmetry is halfway between the zeros. So we sketch an axis of symmetry here. And now we can sketch a parabola that comes down through here. It's its low point on the axis of symmetry and comes back up here. So there's kind of a graph of this function. Okay. Not a great graph. I kind of missed some of my points and the shape isn't quite right, but still representative. Okay. Well, let's now take another polynomial about this. There are 3 points on the graph of this polynomial that I can immediately sketch. Take a second, write down on your paper the easiest 3 points on the graph of this polynomial that we could sketch. Okay. So, well, easy point to get, you let x equal 0. For most functions, or for a lot of functions, you see, it's pretty easy to figure out what you get when x equals 0. That's fairly easy to multiply out, but yeah, you want to write it out like this. You want to write a logical step to, again, remind yourself that you're letting x equal 0 and you get a y value, right? Otherwise, you might make the mistake that I saw one person making, called that an x value. Well, it isn't, x is 0. So you want to write it out. You want to document what you do. It doesn't take that long, and you learn more per unit of time, even though you take a little more time. And on the whole, you end up learning faster. Okay, so you want to get in the habit of trying to write things out the way you see me write them out, or something along those lines. Okay, explain it to yourself the way I'm trying to explain it to you. Okay, now, you get y equals 0, let x equals 3 or -4 or 7. And that's obvious. 3 makes this 0, 7 makes this 0, -4 makes this 0. So our points this is the y-intercept, which occurs when x equals 0. These are the x-intercepts. These are the x-intercepts. They occur when y equals 0. Why are these x-intercepts? Because their y-coordinates are 0. Y-coordinate is 0 on the x-axis. So -4 is 0. We'll put that here. Three, 0. And 7, 0. And then we have 0, 84. Well, the y scale doesn't have to be the same as the x scale. And that's a good thing, because 84 would be about 12 times higher than this, which would be a little higher than I can jump. Okay. Now I can't jump all that high. If I really tried, I doubt I could jump high enough that my waist would be even with the ceiling. I really doubt that. What would that be? That would be a 60-inch vertical jump. Anybody can do a 60-inch vertical jump? I've seen people who do in the 50s. Okay. And the person I saw I could do in the 50s was a professional basketball player. He was about 6'7". Didn't play in the NBA, played in one of those leagues where he's played on every continent, stuff like that. He's good. They make good money. Anyhow, there we go. He owned the gym I go to back for a while in the 90s. Okay. Okay, anyhow. Jumping ability aside, we really don't want to use the same, because I could probably jump high enough to get 84, but there's no board up there. Okay. So I'm going to put 84 here. So that's the point 0, 84. That's my y-intercept. Well, you know what? Ain't no way I'm going to draw a parabola through those points. Okay. If I draw a parabola, it goes through here and here and here. Then I'd have to turn around and go through here. It wouldn't be a parabola anymore. It'd be a wiggly thing. Okay. I could do a little more reasoning. And I can reason out that if x is a really big positive number, well, even if x is bigger than 7, then all three of these are positive numbers, right? Okay. So if x is like 10, well, I'd have 3 here, I'd have 14 here, and I'd have 7 here, right? 7 times 14 is 98, 3 times 98 is 294. Yeah. Okay. So I'd already be up to 294 if I just went out to 10. You do that arithmetic yourself. You might have to write it out, but there it is. So 294 would be, well, on this scale, 84 is there, 162. We'd be up about here, just by the time we get to 10. And if we keep going to bigger numbers, we're going to multiply all three of those numbers. They're going to get huge really fast. So what's going to happen on this side is this thing's going to go up real fast. Or it's going to go down real fast, actually. No, it's going to go up real fast. Okay. On this side, if my number is less than -4, all these numbers are going to be negative. Okay. If x is -5, that's -8, that's -1, and that's -12. If x is less than -4, well, the biggest number is going to be x plus 4, right? It's already negative, and these are going to be negative. And then if I go into big negatives, it's going to start going down real fast. It's going to do this. Now can I draw a picture? Yeah. Okay, well, draw those points and draw a big arrow here and draw an arrow here and sketch me a nice smooth curve that goes through those 3 points, goes down fast here, goes up fast here. And it doesn't go through the x-axis any place but here, here, and here. Because the only place y can be 0 is if one of these is 0. If none of these is 0, then I'm multiplying 3 numbers and none of them are 0. I'm not going to get 0. Okay, so it can't go through the x-axis any place but at these 3 points. Are we ready? Not for the dance. You're never ready for that. Okay. Okay, so I'm going to do it. Now, notice that when I drew this arrow, it's a subtle point, but I'll just make it clear. The thing gets steeper and steeper as it goes down. So it doesn't ever curve back like this. It just drops off the cliff, keeps getting steeper. And same thing over here, keeps getting steeper. Okay. I can prove that using calculus. So we're not going to prove it, but it's easy to prove. Look calculus. And just a little, it'll take that much. Okay, so I'm going to come up through here. Down through here and back up through here. Now, the one thing that I did that you didn't is I didn't try to make this the highest point. Okay. There's no point in trying to make that the highest point. You draw the smoothest curve you can. And it's a little ambiguous where the high point is or where the low point is. It's very easy to find that point if you use calculus. Okay. Very easy to find exactly what point it's lowest and what the coordinates are and what the coordinates of this point are. Okay. But we're not going to do calculus. I'll leave that adventure to you for when and if you take calculus. Okay. Yeah, again, I do recommend if you do reasonably well in this course, an applied calculus course would be beneficial for most people. And isn't all that difficult. The engineering calculus is a bear. You don't want to take that unless you're really ambitious. Okay, so there we have it. There's a graph of this polynomial. Now, what if I vertically shifted this polynomial just a little bit? I'm going to do this. If I vertically shift it this much, enough to just bring this point up to where it just touches the x-axis. So then, if I brought it up that much, let's see, let's just say this point and this point and this point all go up this much. So I'm going to draw a little arrow about that long. Say that all these points are going to go up this much. And this point, of course, is going to go up that much. So I'm going to go through here. So I have a point here. And a point here, and a point here on the new graph. And also the point where this thing hits the low point, since I raise it just enough to bring the low point up to the axis, is going to just touch the axis. The whole thing still has the same basic shape, but it looks kind of like this. Okay. If I do that, then the point where this touches the x-axis is temporarily a parabola. Okay. Close to this point, it's very close to being a parabola. Okay. So we can have a point where on the x-axis and x-intercept where the thing just kisses it, touches it like a parabola. Or it could touch it like a cubing function or any other type of function. It's going to be like a power function when it goes through or touches the x-axis. Now the power function here, it's just a linear function. Okay, so y equals mx plus b is it goes through here or here or here or here. Yes, slope is like this, slope is like this, slope is like this. And I'll actually draw little segments. Just, you know, we're not going to have to remember this we're thinking about it. Right there is a linear function that pretty well models this. Right here is a linear function that models this. And here's a linear function that models this in the vicinity of each of these points. Okay, and that's actually a big deal. And down here, there's actually a parabola. Just a small little section of a parabola here. It's a good model for the function at this point. There it is. Okay, well, that's kind of an overview sketch of parabolas. If you understand, or polynomials, if you understand that much, you've got a really good start, and polynomials shouldn't be too difficult for you. Okay, so it's worth thinking about these things.